Hi everyone and welcome. So today we're going to dive into this really fascinating puzzle from the world of chemistry. It's a kind of identity crisis that happens at the molecular level, and it's all about how the exact same ingredients can end up creating totally different things.
I mean, think about it. What if you had the exact same number and type of ingredients for a recipe, and yet you somehow ended up with two completely different dishes? Well, it turns out in the world of chemistry, this kind of thing happens all the time.
Okay, so take a look at these two molecules. You see they're both made of the exact same stuff, 4 carbon atoms and 10 hydrogen atoms. Same parts list. But one of them is butane, the fuel in a regular lighter. The other is something called 2-methylpropane, which is a refrigerant gas. So same parts, but one helps make fire and the other helps make things cold. How is that even possible?
Well, the answer to this whole puzzle has a name, and that's exactly what we're going to unpack today. Let's meet the isomers.
So here's the deal. The phenomenon is called isomerism. It's basically when compounds have the exact same molecular formula, the same shopping list of atoms, but the atoms themselves are just arranged differently. And we call these different compounds isomers. So you see, with molecules, it's not just what you've got, it's how you put it together that counts. This is actually a perfect way to think about it. Just think about the letters A, T, and E. You can arrange them to spell AT or EAT or T. It's the same 3 letters, but you get totally different words with totally different meanings. That's exactly what isomers are. They're like the anagrams of the chemical world.
So here's how we're going to tackle this. First up, we'll get into molecular isomers, and then we're going to uncover something even more surprising, isomers that exist at the nuclear level.
Okay, let's start with the most common type, which are called structural isomers. This is where the atoms are literally wired together in a different sequence. It's kind of like having the exact same pile of Legos, but you use them to build 2 totally different things.
So, the big takeaway here for structural isomers is that they have a different bonding sequence. The actual blueprint, the wiring diagram for the molecule, is different for each one. And hey, check it out. This brings us right back to our first puzzle. This specific type is called chain isomerism. With butane, you've got those 4 carbon atoms lined up in a neat little row. But with 2-methylpropane, see how one of the carbons branched off? Same parts, just a different carbon backbone. Okay, but what happens if the main carbon chain stays the same? Well, sometimes the only difference is where a certain feature is located. And yeah, you guessed it, we call this position isomerism. Look here, both of these molecules have a 4-carbon chain and a double bond. The only difference? In but-1ene, that double bond is at the very beginning. In but-2ene, it's right in the middle. Same piece, just a different spot on the board. Now, this next one is where things get really, really different. This is where rearranging the atoms actually creates completely different types of chemicals. So get this. With the formula C2H6O, you can make ethyl alcohol. Or, with the exact same atoms, you can make dimethyl ether. One is what's in alcoholic drinks, the other is an industrial propellant gas. I mean, wow, that really shows you the power of just arrangement. Okay, so we've seen what happens when the connections are different. But what if the connections are exactly the same? What if the basic blueprint is identical? Well, that's when we get into a more subtle, kind of 3D version of this puzzle. We call them stereoisomers. And this is a huge deal in things like biology and medicine because a molecule's 3D shape is everything.
Right, so just to be clear, with stereoisomers, the atom-to-atom connections are the same. The only difference is their 3D arrangement in space. So we're not talking about the 2D blueprint anymore, we're talking about the final 3D structure. And honestly, that can be the difference between a drug that saves your life and one that does absolutely nothing.
A perfect example of this is something called geometrical isomerism. You remember that double bond we saw before? Well, it acts like a rigid bar. The atoms can't just spin around it. And because of that, other atoms can get locked into 2 different positions, either on the same side, which we call cis, or on opposite sides, which we call trans. The connections are identical, but you get 2 unique 3D shapes with different properties. You've probably even heard of this with cis fats and trans fats in food. It's the same idea.
So, up until now, we've been talking all about arranging atoms to make different molecules. But what if I told you this whole idea of different arrangements of the same stuff goes even deeper? I'm talking all the way down inside the nucleus of an atom itself.
And that brings us to our final, and maybe the most mind-blowing twist in this whole story.
nuclear isomers.
Okay, so this is where it gets a little wild. A nuclear isomer isn't about different atoms. It's about a single atomic nucleus. It has the same number of protons, the same number of neutrons, but it can exist in different energy states. It's literally the same nucleus, just, with a different amount of energy packed inside. Let's look at cobalt-60, for example. Both of the forms you see here have the exact same number of protons and neutrons, but that version with the little m next to it, M stands for metastable, is in a higher, more excited energy state. Eventually, it'll relax and fall back down to its stable ground state, and when it does, it releases that extra energy. Pretty amazing, right? Same nucleus, just two different energy configurations.
So there you have it, from the gas in a simple lighter all the way down to the energy state of an atomic nucleus. This idea of isomerism shows us one crucial thing. Arrangement is everything. Just a tiny change in how things are put together can create a completely new reality. And it really makes you wonder, right? What other hidden structures and secret arrangements are out there, quietly shaping the world all around us? Something to think about. Thanks for joining me on this one.